All right, we'll continue with our establishment of the matrix vector weak form. Before we sort of plunge onward, I should just clarify some notation. So I know I used the following symbol. I've been using this symbol. I probably said what it means, but let me make completely clear. This symbol is since or because. Right? I realize it may be slightly archaic notation that has fallen by the wayside, but I tend to use it still. Okay, so that's where we are. Let's continue then with the matrix vector form. What we did in the previous segment was write out the important contributions that arise from the weak form for a general element, right? And we consider the two main integrals that arise in the weak form from the integral that remains on the left-hand side, as well as the one that the one on the left-hand side which comes from the stress, and the integral that's on the right-hand side that arises from the forcing function. We wrote these out for general elements. What I'd like to do now is take the step of just sort of particularizing them for the first element, right? Because of the fact that it has that Dirichlet boundary condition. Okay, so note that for E equals 1, okay, we have integral over omega E WH comma X sigma H A dx. This is simply C2E multiplying E A over HE, right, times, let me see, how does it work out now, right, correct, this times minus 1, 1, D1E, D2E. Okay, right, and you can actually see this in a very simple manner by just taking the general expression for a general element E and recognizing that C1E is not present in the expansion for element 1. All right. Likewise, we get integral over omega E WH F A dx equals, in this case, it's just a scalar, right? In fact, well, actually, all the integrals do turn out to be scalars when we complete the matrix vector products, okay? But in this case, we don't even need to use matrices and vectors. So the forcing term is just C2E. We have F A HE divided by 2 times 1. Okay, so those are the contributions from element E equals 1. All right, what we are aiming to do now is pull everything together. We are going to use the same approach as we used in going from summations over the degrees of freedom for each element integral, except that we are going to now apply that idea to the sum over elements. Okay, and in doing so, we are talking of the following of the following complete weak form. Okay, so yet again recall the finite dimensional weak form. It's this: sum over E, integral over omega E, WH comma x, sigma H A dx equals sum over E, integral over omega E, WH F A dx plus, let's not forget this term that we have not had to worry about for quite a while, right? The term coming from the Neumann boundary condition. So what we spent our time in doing over the last segment was expressing these integrals, right, in a more compact form using matrices and vectors. So what we now have is the following. We have the term above implies a sum over E, sum over all the elements. Now, for the general case, we have a form which involves a matrix vector product. So actually, let me do one thing. Let me first write out the contribution for element 1, okay, the special contribution for element 1. For element 1, we have C2E, but E is 1 for element 1. Okay, E, A, H, E, but that's H1. Okay, times minus 1, 1, multiplying the vector D1, 1, D2, 1. Okay, and recall that when we write D1, 1 and D2, 1, the superscript there refers to the degree of freedom for that element, and the subscript refers to the element number, right? So this is the contribution from the first element to this integral, right, to this integral. Okay, for the other elements now we have the sum E equals 2 to NEL, okay, of C1E, C2E, E A over HE times this very simple matrix 1 minus 1 minus 1 1 multiplying D1E D2E. Okay, so those two contributions, the special contribution from element 1 and the contribution from that sum E going from 2 to NEL, give us that integral that shows up on the left hand side involving the stress, okay, the stress and the gradient of the weighting function. Now this is equal to all the right hand side terms, and the right hand side terms also I can write as follows, right? Again, as we did for the integral on the left hand side, I will first write the contribution from element 1. That contribution is C2 for element 1 times F A H1 over 2, where the H1 reminds us that that is element 1, plus a summation E equals 2 to number of elements Okay, and that summation then is okay. That summation gives us C1e, C2e, F A H E over 2. Okay, all right. We get this contribution, and let me see, do we, oh sorry, we have F A H E over 2, and we have F A H E over 2 again, right? Okay, there we go. That's complete. Now, the terms we've written on the right-hand side are the ones that arise from that integral. Okay? And the term that we could safely not have to worry about when we were writing out these matrix vector contributions is that one, because that appears only at a single point. It just appears at the point on which we have a Neumann boundary condition. Okay? Now, we recognize that that term alone, WH at L, has a very specific, very simple representation. Can you think of what it is? It is C2 for the very last element, E equals N EL. Okay? So, the term that we add on here is C2 for the very last element times the data T, which is the Neumann condition on the traction, times the area. Okay? This is it, really. This is a nice compact representation of our finite dimensional weak form. This is everything. One thing that may be useful for me to point out here is related to why we get this simple representation. Okay? It's a fairly straightforward thing, and it's something that you may all already have noticed, but it's useful to point it out. Okay? So, remark. And this remark goes all the way back to our representation of UH in an element as being the sum of NA. Let me write NA as a function, expressed as a function of parameterized by XC, times DAE, and also to the corresponding representation for the weighting function. Sum over B, NB, C, C, B, E. All right. Of course, it's implied here that X is, though I've written this on the left-hand side as X, it's really X parameterized by XC. Right, and the same thing here. The same thing here as well. Okay, so now observe that, so this is of course for a general element which is written as, which can be depicted as this. We would have omega E. Here we would have X E. We would have X E plus 1. Those would be the global node numbers, right? And we recall that this comes from a bi-unit domain, which is -1 to 1, and that is 0. This is omega C, right, in the one-dimensional space parameterized by xc. Okay, now, okay, so we have this picture, and what I'm going to use it to do is to ask ourselves what form these expansions take for UH and WH if we choose to evaluate these quantities, these fields, at the nodes themselves. Okay, so let's suppose that observe that UH at x equals xe, all right, is basically UH at x evaluated with xc equals -1, right? It's the left end of the element, right? It's the left-hand side node, which in the omega xc space is represented by xc equals -1, right? So this then is sum over A, NA evaluated at C1, right? Because remember, C1 in the omega xc space is what we identified as being equal to -1, right? So it's NA evaluated at C1 DAE, okay? But then we recall that that these basis functions we've constructed have this Kronecker delta property, right? So this is essentially the Kronecker delta A1. Okay? Okay, and therefore apply to DAE, this becomes equal to simply D1E. Okay? Right? Essentially what we've done here is to observe that if we want to evaluate the trial solution at the left node, right, it's effectively the first node of this element, what we get is that the trial solution is indeed equal to the degree of freedom corresponding to that node. And the same thing happens if we want to evaluate UH at xe plus 1. This is equal to UH at x with xc equal to 1, okay? This is equal to sum over A NA xc2, recognizing that xc2 is the point xc equals 1 times DAE, okay? But then this again becomes delta A2 by the Kronecker delta property of the basis functions. And therefore this, when applied to DAE, gives us D2E. Okay? All right? Essentially, the Kronecker delta property ensures for us that the trial solution evaluated at the corresponding node is indeed the degree of freedom value at the node. Okay? Stated differently, the nodal degrees of freedom are indeed the trial solutions themselves using these particular basis functions. Okay? So, and the same thing, by the way, happens, of course, for WH as well. I won't go through the details, but WH evaluated at XE is equal to C1E, and WH evaluated at XE plus 1 equals C2E. Okay? So the remark here is that the Kronecker delta property the Kronecker delta property of the basis functions right, and by this we mean the specific basis functions that we're working with, right? The Kronecker delta property of the basis functions ensures that the nodal degrees of freedom, right, which are these ones, right, or these for the weighting function, right. This ensures that the nodal degrees of freedom of the solution field are indeed its values at the nodes. Okay. This is sometimes called, this is sometimes referred to as the interpolatory property of these basis functions. It is not a universal property of arbitrary basis functions. We have specifically chosen basis functions that give us this property. All right? Okay, why did I need to say all of this? I needed to say all of this because it is what we are using here. Okay? We're using it in particular in this, to make this identification of WH at L being equal to C2 for element NEL. Okay? All right. So we have this, okay? And this is the reason we're able to do that. Okay? Fine. What we want to do here now is go back to what we had when we put together the finite dimensional weak form, when we made all these observations about how it can be written out in terms of the matrix vector products. Okay, you have it on your notes, and thanks to the technology here, I have it in front of me, and you can't quite see it, but I can see that I have it here. Okay, so what I want you to do is go back to your notes to the point just before we made the slight digression to talk about this Kronecker delta property of the basis functions. Okay, go back to how we'd written out the weak form. Okay, and we are going to work off there. Okay. All right. So if you look at the way I've written out the finite dimensional weak form just preceding this, this remark, you will see that we are now able to pull things together from there. Okay. And in order to pull things together, what we need to do is to observe that there is a mapping between the degrees of freedom as expressed using local node numbers and global node numbers. Okay, so note that the following map holds between local and global node numbers or local and global degrees of freedom. Okay, I will express this map first in terms of the degrees of freedom that are used to interpolate the trial solution. Okay, so if we have this particular local degree of freedom, and recall that this refers to local degree of freedom A in element E. Okay? This can be written as global degree of freedom D E plus 1. Okay? Let me see. So DE plus 1. Sorry, it's not DE plus 1, it should be DE plus A minus 1. Okay, so this, let me write out in words what this means. On the left hand side, I have local degree of freedom A in element number E. Okay? That's what this refers to. On the right hand side, I have global degree of freedom number E plus A minus 1. Okay? Let's check that it works. It's always a useful thing to do, right? So let's just check right here. Okay, so let's suppose we are in element 1 and we are talking of the first degree of freedom. Okay, that would be D1, 1. That is the same on the right hand side for the global degrees of freedom. D, E is equal to 1, A equals 1, so we get D1. Okay, likewise, D2, 1 is equal to D, E equals 1, A equals 2 minus 1, D2. Okay, and this goes on. Let's check what happens in the very last element, right? So when we have D1 NEL, this is equal to, now E equals NEL, A equals 1, so we get D NEL, and D2 NEL is equal to global degree of freedom, E equals NEL, A equals 2, we get D NEL plus 1. Okay, this works out because if we look at our domain, right, and this is the very first element, right, this is omega 1, right, I will write up here the local degrees of freedom, right. The global degrees of freedom for this are D1 and D2. Okay. For the very last element, which is this one, right, this is omega NEL. The local degrees of freedom here are D1 NEL and D2 NEL, and here we have D NEL, D NEL plus 1, right? Makes sense. We have one node more than the numbers of elements, right? The total number of nodes is one more than the number of elements, and that is borne out by the way things work out here. Okay? All right, and of course the same thing holds for the other ones also. Right, similarly we have C A E equals C E plus A minus 1. All right. So we made this made the observation about this mapping between local and global degrees of freedom. We will use this to go back to that weak form that we had written out in terms of matrix and vector products over each element, and carry out an important process of finite element assembly. We should probably do this in the next segment though. Okay? So we'll come back to this in just a little bit.